In this class, we are going to talk about carbon hybridization. Carbon has the atomic number 6, so it has 6 electrons. Its electronic distribution is one sp2s22p2. When we put this on the energy diagram, we can verify that it has only 2 unpaired electrons. For this distribution in the energy diagram, it should make just 2 bonds. However, all carbon compounds have 4 bonds. So how can we explain this? Atomic orbitals are described as wave functions, which are mathematical functions. So, different atomic orbitals can be mathematically combined to create new orbitals that are called hybrid orbitals, as it is a mathematical combination, in fact a linear combination. The number of orbitals before and after must be conserved. So, when it comes to hybridization, always check the orbitals that were used at the beginning and the hybrid orbitals at the end. For energy reasons, only the orbitals of the outermost layer are used in hybridization. So now, let's see the sp3 hybridization of carbon. Our focus will always be on hybridization from the energy diagram. For this hybridization, we will use 1 2s orbital and the 3 2p carbon orbitals. So, starting from the electronic carbon distribution, we will combine these 4 orbitals to form 4 new hybrid orbitals. Note that these 4 orbitals have the same energy. That is, they are degenerate. The 4 electrons that previously occupied atomic orbitals must now be redistributed in hybrid orbitals. Note that the number of orbitals, as well as the number of electrons, was conserved before and after hybridization. This orbital will make only sigma bonds, which are simple bonds. All carbon compounds that make 4 simple bonds are tetrahedral. This is the representation of the atomic orbital P before hybridization. After hybridization, taking an isolated hybridized orbital, it looks like this. And this is the sp3 orbital that has tetrahedral geometry with an internal angle of 109.5 degrees. In addition to the sigma bond, carbon can also make the pi bond, and for that, we need sp2 hybridization. In this hybridization, a 2s orbital and T2p orbitals will be used whenever it is necessary to hybridize. This process of assembling the diagram has to be repeated. So, now, we are going to use the 2s orbital and T2p orbitals, but the choice is not random. We need a semi-filled orbital and an empty orbital. We do the hybridization to generate 3 hybridized orbitals, and these 3 electrons that previously occupying the atomic orbitals will be distributed in the 3 hybrid orbitals. The p orbital that has not been hybridized remains unchanged. At the beginning we have 4 orbitals with 4 electrons, and we end with 4 orbitals and 4 electrons, 3 of which belong to the sp2 orbital and 1 to the p orbital. Note that there is an energetic difference between the p orbital and the sp2 orbital. In this hybridization, the sp2 orbital is responsible for making the 3 sigma bonds, while the p orbital will make a pi bond. As we have seen, the p orbital had greater energy than the hybridized orbitals. This will have important consequences on the reactivity of the compounds that have sp2 hybridization. The presence of the pi bond prevents free rotation around the sigma bond, and this has important geometric consequences in classes such as alkenes. This is the shape of the sp2 orbital, which has a trigonal geometry with an internal angle of 120 degrees. These are the orbitals of a sp2 hybridized carbon, in which the sigma bonds will be made by the hybridized orbital, while the pi bond will be made by the non-hybridized p orbital. There is yet another hybridization that carbon is capable of, which is sp hybridization. In this hybridization, we will use only a 2p orbital with a 2s orbital, and it will be the empty 2p orbital, which after hybridization will form 2 hybrid orbitals. Next, we will keep the 2 2p orbitals unchanged. So we had 4 orbitals at the beginning with 4 electrons, and we now have 4 orbitals at the end with 4 electrons. 2 of them are unchanged p orbitals, and the other 2 is the hybridized sp orbital. The hybridized orbitals continue to make sigma bonds, so now there will be 2 sigma bonds. And the p orbitals will allow 2 pi bonds, which can be a triple bond, or 2 double bonds. This is the shape of the sp orbital that has linear geometry, with an angle of 180 degrees. And this is the aspect of a hybridized sp carbon in which the sigma bonds will be made by the hybridized orbitals and the pi bonds are made by the non-hybridized p orbitals. To summarize, it is important to always observe the initial and final number of orbitals, as well the electron ones. This number must always be conserved. Each hybridization has its own geometry. This is very important because it has a direct impact on the properties of the substances with each hybridization. sp3 hybridization has tetrahedral geometry. sp2 hybridization has trigonal geometry, and hybridization sp is linear geometry. Whenever there is a hybridized orbital, it will make the sigma bond, which is a frontal bond, while whenever there is a non-hybridized p orbital, it will make lateral interaction for the formation of the pi bond. Thanks for watching. To receive alerts on more organic chemistry videos, subscribe to our channel. See you in the next class.